Hello, programmers. This is Ritesh. I'm Ritesh, and I just want to go over our turret subsystem code again, just to make sure we get everything covered. Because this is kind of important. I kind of wish every programmer would know exactly how this works. That's the reason why we are developing these videos for you guys. So let's start with like looking at our turret. Sorry, by the way, this is my CAD right now. This is also computer aided design. Okay, I'm using computers to design. Okay, no. Okay, so this is kind of what I created with my 10 minutes. This goes over everything that we should need. I mean, that's kind of all we need, right? So this is the top view. If you look the robot from the above, this is how it looks like. This is your limelight, that's your turret, and blah blah blah. We do not care about what motors these are, how the CANcoders. That's not our part. We are turret, okay? But these two numbers are basically how many. What's the offset? This is the center of the circle. What's the offset of the limelight? So apparently, this is something that I made up. This is not true. It's actually quite different. This is 3 inches to the left, and then no, 2 inches to the left, 3 inches forward. That's where our limelight is. Is it in a specific angle here? Not really. It's straight. So that kind of makes things a little easier. And this is your front view. This is kind of what you would see. Obviously, this is not accurate at all. I just want to make sure that we have enough information that we can start programming. These numbers are all made up. I'm not sure whether CAN ID21 is available. We might need to change it in our robot, but we need some example numbers. So 10 inches right here is from the limelight's lens to the ground. So that's 10 inches. And obviously, arm center of the circle to the limelight is 2 inches. I also have given CANcoder. They're not CAD IDs, CAN IDs. I might need to change that later. So CAN ID is 31, and that's your motor. That's CAN ID is 21. So let's actually start programming, like right now. I use IntelliJ, but honestly doesn't matter. This is our Robot Challenge 2025's GitHub account, I mean repository. So I can just get started. In subsystems, I do new FRC, I create a subsystem. Okay, since I'm gonna create a turret subsystem, I'm just gonna say turret. And then, yeah, sure, I don't really need that. Subsystem base, yep, that's my parent. Okay, cool, we have that. We got a good setup right here. I don't really like the green text, so I'm gonna delete it right now. Oh, by the way, I would like you guys to like follow me through your own code. So like put my video in a separate monitor, mobile, and then try to code it with me. You know, that would be better for you guys. Also, every subsystem comes with a default function called periodic. I don't think the uh, IntelliJ's program added it for me, so let me add it for me. Public void periodic, if I can spell it correctly. Okay, that's kind of all I need. And by the way, this is gonna be state-based system, so we will go through states. So let's actually start with states. So let me just do all my states together. So public enum, and it's gonna be turret state. Okay, let's think about the states that a turret could be. Okay. Immediately, the two things that should come to mind is if your turret is stopped or if your turret is idle. I mean, aren't those the same thing? Yeah, those are the same things. What am I speaking? Okay. Uh, I kind of want to make up some states. One is idle. Idle meaning it doesn't do anything; it just stays there. That's like its default position. Idle should be the one when the robot starts. So that's its default state. Okay. So let me type in idle. Uh, it doesn't have to be capitalized. I like capitalizing stuff. Also, let me turn off AI. I don't really think I need AI. AI is a good source, not when you're teaching or not when you're learning. Enable completions. I thought I disabled you. Oh, it's disabled. What is this then? Well, I can't really disable it, can I? Okay, I can't really disable it. I think it's by default by IntelliJ. Okay, idle. I might need like a state where it just spins forever. Don't ask me why really. I just like making things spin. It's fun. Okay, so idle, spin, and this is where we can actually make some good states. How about find targets? So it basically spins in a slower rate until it finds a target. Yeah, I think that's a good idea. So I'm gonna add it right now. Find target. Um, Another function um, might be track target. Like if it finds a target, then it's gonna track no matter where it goes. Yeah, I like it. I like it. So track. I spell it correctly. Yeah. So those might be your states. Honestly, that's good enough. Okay, that's good enough. Now let's like actually initialize some of our variables. When I meant variables, I meant um, all our mechanisms. So we have a CANcoder, we have a Kraken. So let's start with that. Okay. So to initialize, I'm pretty sure all of you would know. Just private or public. I like to make my things private. The only reason I made it public is so that I could like access this state in my robot container. But here I can just say private TalonFX, and also it's actually good to like make things private. No one's gonna steal your code anyways, but it's usually a good practice. And this is gonna be our turret motor. We can initialize this right now, or we can just wait until we hit constructor. So we can just say private TalonFX start motor. Good enough. And also we have our CANcoder. So let's quickly type that out. Private CANcoder, and then we can say turret. Turret encoder. Sure, why not? Oh my goodness. Turret encoder. Sure, that works. That's all your electronics. So let me just add on electronics. Mm, yep, that's good enough. And now we should also have something called a current state. It's a variable. So what we are going to try to do is we will have a function that will change the current state. And our periodic basically looks for what current state is and then runs functions based on the selected variable. Um, Actually, let me think about that. It's gonna be hard for you guys to like read my mind right now, so we'll wait on it. But we'll explore these things a little bit more. We have our Limelight helpers, three bays. Okay, okay. Um, we should make a constants file. Let's quickly make a folder and then name it constants. Or or we can just make a file that that's like our robot map. Actually, I don't really want to go through that. I'm just gonna put all my constants in here. But it's definitely appreciated if you can make a separate class, a separate file called constants.java, and then put all the constants there. So you have one file to edit the entire configurations of your robot. We are not doing that here. Okay, we are not doing that. Okay, let me just have my integers. So let's look at how many constants we have. We have one. This is from your Limelight lens. This is your altitude of your Limelight lens, basically, right? That's your difference between the center of the circle and your limelight, and then that's your forward distance or vertical distance. Okay, we have like three constants. Cool. So we can make it final, right? The only reason I'm okay with making this final is because I'm never going to edit it, right? So we can just say double um, camera cam offset. I'm just going to go with that. Actually, I don't like the capital letter. Offset x. So x is this guy. That's 2. We can make it 2. And then this is going to be y. And then we can make it 3 according to our chart. Cool. Okay. There are a couple more things we can have. We should have actually. Um, so this is gonna be private final double limelight. So limelight height or limelight's altitude. So it's not actually altitude. It's just the height from the ground to the limelight's lens. So for us, it's gonna be 10 inches. And by the way, if you guys don't know, everything here is in inches. Just to make things easier, I guess. We can make it all into centimeters, but I don't really want to do that. It's too much work. We can do that. You guys can do that in your own time. All right now. Okay. Okay. Now let's actually initialize a couple of these variables, our third motor and third encoders. It's pretty easy. Just say third motor. It's just new TalonFX, and then according to our chart, it is 21. 21 inch. Okay. And then third encoders is 31, not 21. Cool. That's that's a good initializing variable. And anytime you have a motor or a CANcoder, these these functions should be like basically it should roll up immediately. One is your start motor with a variable speed, and then stop motor, and then your get angle. Okay, the angle should come from our CANcoder. Okay, so let's actually get this started. So public, this can be public because we want other subsystems to like interact with this. Public, it's gonna be void. It doesn't need to return anything. Start motor. Start motor. Since I wanted to I want to start at different speed. I can just have double speed, and then I can just say turret motor dot set. Yep, that works, right? If I make the speed as 0.5, it just runs the motor at 50% of the speed. That works. That works. We can also have something called stop motor, which basically just does the start motor dot stop motor. So you might think stop motor would just be start motor at set speed equal to 0, but it kind of does things different. I think it actually stops the motor. It actually puts the brake on it and stops it. So we'll just use this. I mean, I don't see why set speed equals 0 wouldn't work unless there's some momentum carrying over, but Usually, just use this. And then we'll also have a get angle. This is going to return a value, right? So it's going to be double public double get angle. And then this should be our, I guess this is going to be, yeah, this is going to be getting the angle from our turret encoder. Turret encoder dot get position. The reason why I can choose get position is if you hover over get position, it tells you that it's giving you a unit measure angle. That's exactly what we needed. Or actually, get absolute position. That's what we need. Get absolute position dot get value as double, right? And then we can just return it. If we can return that, just like this, and you're fine. Now your turret encoder would just give you the angle. Okay, so most of our skeleton methods are basically done, but we need to add a little bit more. Okay, we need more information, right? So in my previous videos, where I actually talked about the simulations and how we are gonna go and do these turrets, that formula, we're gonna apply that formula. That formula requires a number of things. It wants what the limelight dx variable is. It wants the distance from the limelight to your target. So we need to create a distance formula basically. And then it, yeah, yeah, that's kind of all it needs. So let's actually get started. Okay. Um, I'm gonna pull up a old picture from Discord. Hopefully it doesn't show it. Hopefully I can explain that in a really quick manner. Um, oopsie. Okay, let me just pull up that specific image. Um, Programming. Come on. Okay, so this is the function that gets us our actual angle measure, right? Angle on which the turret should turn. So it needs -1 and 2. If you don't know what -1 and 2 is, it's basically the offset. -1 is offset here, +2 is offset here. As you know, it's going to be different in here. It's going to be 2 and 3, right? Okay, now we should actually get our distance formula. Um, this should be pretty clear. I don't want to explain it, but there's a lot of formulas online that you could use. So public double get distance. Let's just have a distance function. So this distance function needs a couple of things. It needs, um, well, I guess it needs what the tx variable is from the line, or ty variable is from the limelight. So honestly, let's put a pause on it and we'll actually talk about limelights. So obviously, limelight gives us four important variables: tx, ty, ta, and tv. Tx is the horizontal angle. So if you have a target in its view, Tx basically measures how many degrees uh, is the target from the origin of the limelight. Ty is basically the vertical, right? How many degrees it is in the vertical axis. Ta is the area it's taking in its viewpoint. TV is a Boolean variable. It basically tells you if it sees a target or not. It's kind of useful. It's very useful actually. We'll use that. Okay. So I'm just gonna add two doubles and a boolean for tx, ty, and tb. We don't really use ta very often because we don't have to according to our context. So we'll just have those variables private. It's not going to be final because it's going to change every time you move the robot. So private, so I'm not going to make it final. Private double dx, private double dy, and then private double dv. Okay, cool. Now, we haven't initialized yet because there's a good reason why we haven't. We will initialize that in the periodic. Since periodic runs in a loop, what we can do is using a library called Limelight Helpers. This is developed by the Limelight guys. This makes much easier. This makes it so much easier. We don't have to work with any of these network tables as of now. We will work on it later in the season because we will be using it to communicate between systems. But it's pretty simple. You basically say tx, right? We'll initialize tx. Tx is just Limelight helpers dot get tx, and then it asks you for a string. You can just say Limelight. Limelight's name is just Limelight. We will be naming it differently, so it might be Limelight Vision, or I don't even know. It doesn't matter. Doesn't matter. Let's just make it Limelight Vision, and then ty it's gonna be the same manner. Get ty. Same with tv. Tv equal to Limelight helper dot get tv, and then Limelight Vision. Oh, there's a error. I wonder what. Well, it tells me that I haven't made it Boolean. That's true. I made a double. I told myself that I'm gonna make a Boolean and I made it double. I guess it happens. Life happens. It's fine. Everything's fine. Okay, but what I'm gonna do is I'm just gonna quickly copy our distance code. This distance code has been posted in operational manual for a while, so I would advise you guys to like go to our operational manual and like look at it. I can probably explain this to you in real life, actually. Yeah, I know, right? But that's basically um, the formula. So goal height inches. That's basically what's the target's height? That's gonna be. This is basically telling you that the target's height is never gonna change, which is true in our case. It's never gonna change. It's gonna be 12 inches, or I think it's 36 inches. Yeah, it's gonna be 36 inches. Minus limelight height inches. So I think we have it here. Limelight altitude. Limelight altitude. And then limelight mounting angle in degrees. Okay, right now our mounting angle is like 0. It's gonna be straight. But if we change it, then yes. But right now it's gonna be 0. So I'm just gonna quickly make it a double. Double limelight mounting angle is just 0. I can just remove it, but just for future case, I'm gonna leave it right here. So we have get distance figured out. Cool. Now we should probably make the function that changes its perspective from the limelight to the turret. So this function gives you our actual degree to turn. Okay. So we can quickly do public double, or it doesn't need to. Yeah, it's gonna return an angle. What am I doing? And then it's gonna be get angle. It's going to be good angle, but that's not what we want. We want to get target angle, basically what angle we should be in. So target angle makes more sense. Just gonna quickly say get target angle. Cool. I don't need anything in my constructor. I can just go inside and type some bunch of stuff. Okay. So first we need a couple of things. We need the distance and we need our px but in radians. Um, because the math is much simpler in radians. Degrees are much more human, but if you're working with machines, I would advise you to like learn radians. It's kind of annoying, but it's very simple once you learn it. Okay, so this is our formula, right? Oh, yep, that's good enough. So x is basically your distance. We have the distance. I'm just gonna just copy over. Okay. What I'm gonna do is I'm gonna do it. Um, yeah, actually, how about this? We'll make this first, and then we'll make this first. Yeah, that sounds about right. Or we can make this first, and then we can make this first. Actually, let's make the opposite first, and then we'll do the adjacent, so that we can just do tan inverse and then get our angle. Okay. So this is gonna be pretty simple, but we do need our distance variable. So let me quickly get my distance variable. Double distance is just get distance, right? Get distance. So this will give us the distance from the robot to the line, from to the limelight to the target, and then we need some tx, but in radians. Double tx, radians is just rad, right? Is just math, and I think it has a yeah built-in yeah math.2radians, and then I can just make it dx. Sure, that works. That works. I don't see why it wouldn't work. Now let's make the opposite side. So this is going to be double um, target x. I mean, this is it's x-axis. This is y-axis. So I'm going to say target x. Target x is just camera offset, right? This is our camera offset. So it's going to be, for us, it's going to be, yes, 2. So I'll say camera offset plus our distance, and then just times it by our sine theta. Math dot sine, and then this is going to be our dx in radians. Cool. Same thing applies here. It's going to be just dy, but that's going to be cosine here. Let me just change that. That's going to be cosine. That's exactly what it is. Okay. This is going to be ty. And then this is also obviously going to be offset y. And that's kind of it. And we can just return the inverse of this. So tan inverse. Return math dot tan inverse. So tan inverse is basically a tan arc tangent. A tan 2 is like really interesting. It basically allows you to get the degree of any number in the unit circle. It's not just limited to 0 to 90, like tan inverse actually does. So it's a little smarter. It has a bunch of poly functions inside it. I can probably send you an image soon about that. But it's going to be target x, right? It's y over x, so it's going to be target y over target x. Is that correct? 892. Yeah, yeah. That's it. That's how you get the target angle. That's the angle the turret should go. Once you get that done, we also need another function called is there target. We need to have a method or a function to let know us if there's a target present. So we'll just say target present question mark. No, we can't have question mark. Um, and then just return TV. TV works, right? That's basically what we are doing. We're just going to return TV. Cool. So once we have that, now we can actually go to more state configurations. So obviously, we need to have some sort of way to tell um, to make us go to a specific state. So let me just create a quick function. Public, um, it's going to be a command, okay? It's going to be public command, and it's going to be set to state. Yeah, that sounds good. Obviously, you don't have to like type every single thing I do. You can change it if you want. So it's going to be set to state, and then it's going to get our turret state. Okay, it's going to get one of these variables right here. I'm going to go inside the inside the method, and then obviously since it's a command, we have to return something. So I'm just going to do this. Return, okay? It's going to be a new instant command. If you ever want to like run uh, if you ever want to run like actual methods or a command line, a normal programming line, then instant commands is your way to go. So just do instant command, you put your lambda sign, and then you can basically type like a normal programming language. So you can say start motor and then 10. That works. That will basically make start the motor if you run this command. But that's not really what we wanted, right? So now we have to really get into our state variables. Uh, our robot only does one state at a time, right? So we need to have something called current state. So private enum, or not enum, turret state, and then I'm gonna name it state. Oh, or current state. So current state. And as I said before, our initializing state should always be idle. We don't want it to do anything when it's just initialized. So in my initializer, I can just say current state is just start state.idle. Okay, so this all it does is it just changes the current state to whatever state we want. Current state is equal to the state. That's kind of it. Now all you need to do is in your periodic you gotta make sure your subsystem acts accordingly. You can really use switch statements for this. I'm gonna use switch statements. Okay, you could use if else too, like if, right, um, current state is equal to idle, then do this. Else if current state is equal to find target, and do this. We can do that. Or we can use our amazing only switch, and then our comparator is going to be current state. That's how we're going to compare everything together. And in here you can have a case. uh, our case might be any of these things. So let me just create a case for spin. Yeah, so what spin does is just it just turns the motor constantly. Doesn't really have a huge doesn't really have a huge issue in there. So I can just say um, start motor basically, start motor and then run it at like really low temperatures, zero point 0.0 or 0.1. Okay, sure, it just runs it. Um, and you can have another case. This is gonna be track target, and then you can do a bunch more of these things. Also, by the way, if you're using switch, you should have this thing called break. This allows your code to just skip everything here and then goes to the next loop. If you don't have this, it's going to run all these functions, all everything. So make sure you add break. Okay. So let's just say track target is just going to stop motor. Sure, that works. And then make sure you break. And then the next is going to be case find target. Yeah, find target. Let's make it start motor, but run it on 50%, 0.5. And then if nothing happens, then it's going to be default, right? So we can say default um, idle. If it's idle, I just wanted to stop motor and do nothing. Literally do nothing. That's kind of it. But obviously, this is not true. This is not, our robot is not going to do this. It's going to do a little bit more than that. Honestly, to make it easier on our eyes, we can also make like functions for those things. Public, this could be void. Public void action for uh, action for idle. Okay, so action for idle. All it's gonna do is stop motor. So you can call stop motor here, and then copy that, paste it in here. Cool. And then I can do an action for find or yeah, find target. Public void um, action for find target. So this is how, at least this is how I imagined. Um, so the the robot, the turret spins until it finds a target and then stops and then goes to idle. If it finds a target, it goes to idle and nothing happens. That's at least what I think we're gonna do right now. Okay. Mm, so I mean, low key, we can just use if statements. I'm gonna make it really easy for you guys. So the find targets is gonna be if, right? If we don't see a target, okay. So I'm gonna make it if target presence is equal to false, right? If there's no target present, then we can basically start the motor. Start a motor and then with a really low speed, even 0.01 even. Obviously my IntelliJ is like kind of pissing me off. It said there's a much better way to do this, which is just to have that. That's how you simplify. This basically means the same thing. It's just a bit more simpler, I guess. So it starts the motor if it doesn't see something. If it does see something, which is going to be else, if it does see something, then we have to stop the motor. And then, mm, Yeah, and then we can basically use a PID to actually kind of like point at it. Yeah, we can do that. So let us make a PID controller. That's gonna control how fast and how slow our motor should behave to um, reach our target position. So we'll actually make a PID controller real quick. Private PID controller, and then just name a controller. Doesn't matter. Okay, so we'll initialize it. A PID controller has three values. Uh, PIND, shocker, I know. Uh, P should be something at least. Some so it's generated 0.05, which okay, okay, that works. That works. But if you actually wanna learn more about PID, I actually surprisingly have a good source. WPILib PID, and then if I just searched up in Google, ba, 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 ba. Um, and then I can scroll up and then look at simulations. Sim. Maybe not. Let me look at PID simulation. PID control. Is that it? Is that it? No, that is not it. Contributing turret sim. Yeah, maybe this is it. Yeah, that's it. So we kind of have basically WPILib made their own version of the simulation we could use. So let's just say this is my target position. I can change the p value to make our motor basically follow, right? And I can actually increase this 0.5. Oh, oh, it's trying. That's pretty close, right? So you can basically tune all your numbers here and just basically replace it here. It works because if you actually do the mass of that specific turret or the arm cancels out. It doesn't matter. So yeah, that's a reliable way. I'm not gonna say it's gonna be like really reliable, um, because it has system noise. You can generate noise, but real life is way worse than computers. So that's there. We can tune it in our computers and just replace this. It should work most of the time. For this specific turret, it works, but I'm not sure. It's also based on the application you're doing. For example, elevators, it doesn't really work because you need some friction and like other coefficients and mu's. But for this, you're fine. Totally fine. Okay, so let's go to our action for find target. If we see a target, then what we want to do is we want to set our motor speed. Also, we should create dead bands. Dead bands are basically you're telling a controller that this is enough. Like you don't have to be exactly on dot. We can basically tell the controller its set point. Set point is its target. If the set point is 0, and then if you're facing 0.001, it's fine. But we gotta set some tolerance level to it. So we'll just do it. It's gonna be controller dot set tolerance. Uh, we can kind of do like 2 degrees. Yeah, that's fine. 2 degrees. If I tell it to go to 0 and it went to 2 degrees, that's not really going to change a whole lot. And if it's more, we can obviously lower it down. No problem. But our target, remember, is 2 inches by 2 inches. That's way more. We can do this. That's fine. It's easy. It's a 2 inch. I think its radius is 2 inch ball. Okay, so that's enough. Okay. Um, where am I? Yeah, 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 find target, find target. So number one, I'm gonna set a set point for it. So it's pretty simple. Controller dot set point. Set set point. Yep. Okay. We are gonna input its target angle. Its target angle, if you remember, it's this guy. No, no, this guy. This is our target angle. This is the angle the turret needs to face, right? So we can enter that, get target angle. Once you have that, we can calculate the number and then we can just make the motor move in that speed. Mm, Start motor and then controller dot calculate, and here you're gonna give the angle that the turret is facing right now at this moment. That's just get angle. That's just get angle. Yeah, that's it for finding target. Once you find the target, so we can make another statement. If, okay, yeah, there's a lot of statements. If controller dot add set point, so that's a boolean. It gives you true or false. If it is at the set point, then you kind of want to change the current state to maybe like idle because you don't really want to move. That's kind of what you do. It's just you try to find the target. If you find the target, you just stop moving. You are facing it. That is for find target. Um, we can now go back to this line over here and then just replace it. Action for find target. That was easy, right? And then now we kind of have to do it for the track target. This is where the robot kind of like, the turret kind of like tracks wherever you go as long as you're not about 360 degrees. Oh yes, we haven't done any protections yet. We should probably do that. Our turret can only spin 360 degrees. It cannot spin more than that. So unless you want to break the robot. Now that I think about it, the spin function wouldn't really work because you can't spin unlimited amount of times. Yeah. Okay. It's okay. It's okay. That's gonna be something that I will cover in my next video. Public void action for uh, track target. Track target. Um, it's honestly just gonna be the same thing. It's just we are not gonna make it go to idle. It's really simple. Copy, paste. We are just gonna remove that. So it always tracks. That's kind of it for today. In my next video, I will talk about limitations because there is a problem here. Is that it spins infinitely? We have to make sure it doesn't spin infinitely. It only can spin from 0 to 360 degrees or 0 to 2 pi. Um, we will change that. Yeah, thank you for watching. I hope you guys understand this a little bit better now. Oh wait, I should probably show you like the how to access that in your robot container. Yeah, I completely forgot that. Okay, so it's gonna be simple. We can make it private or public. I'm just gonna make it private. So our turret subsystem. So it's gonna be turret subsystem. We can name it anything. We can just say turret subsystem. Sure. We can initialize it right now, or we can initialize it in the actual robot container constructor, but I don't care. Boom. And then in our configure binding, oh, completely forgot. We'll also have like a Xbox controller, private Xbox controller or command. Yeah, command Xbox controller. It's not the normal Xbox. Command Xbox controller. Um, controller. Initialize this quickly. Oh, port is gonna be it's gonna be 0. Sure, the first port that's available. And then our configure bindings, we can just say controller dot X. If I press the button X on true, then I want to run. I want to like basically find the target, right? If I press X, so I can just do turret subsystem dot set to state, and then we can literally just pick uh, turret state dot track target. Yeah. Okay. And also this is quite long. Turret subsystem dot turret state dot track target. That's kind of very repetitive, you know. So we can fix this. Honestly, it's kind of easy. We just need to control X this, so kind of remove it, and then we should probably make a new file. We should probably make a new folder and folder called turret, and then add those files inside. But for time's sake, I'm just gonna do this. It's gonna be turret state. Um, sure. Add, and I paste it here. Here. Now everything should be fine. And now container, just remove it, and then make sure you import this guy, and you're fine. You can literally just pick and choose. If I wanted to do something else like find target, I can do that, or track target. That's it. That's kind of the basis of how you can do your state subsystem. Obviously, we have some limitations. We'll talk about limitations. We'll make sure this is bug free in our second episode. But yeah, thank you for watching. I'll try to get this done as soon as possible and post it on YouTube. Yeah, bye.